Ready. Hey there, welcome to assignment 49. Now, you may or may not know this, but my ID tag doesn't say teacher on it. It says mathematician. And so today I am going to induct you into one of the secrets, the fundamental theorem of algebra. Oh my goodness. They had such a parade when Carl Friedrich Gauss, 1777 through 1855, came up with this. He got a parade. They marched him through the streets. They held up, he was sitting in a chair, and they held the chair over their heads as they went down the avenue. Oh, it was such a day because we finally had a fundamental theorem of algebra. So, luckily, you've been studying algebra for a number of years, so I'm sure you're very comfortable with it. Will you take a moment to write down the fundamental theorem of algebra? What's that you say? You don't know it? No, that can't be. See if you remember this little ditty. If f of x is a polynomial of degree n, then f has at least, I just want to say before I write this rest down, full professorship for writing this, okay? Parade through the city for writing this. That f has at least 1, 0, x-intercept in the complex number system. Ooh, mic drop. Yeah, so what's that mean? Well, all it means is every polynomial, be it this polynomial or this polynomial, every polynomial has at least one x-intercept. Look, I got 2 here. Oop, I got 1 there. But you say, Mr. Cooper, that's not true. What about y equals x squared plus 4? Doesn't have any x-intercepts. Never touches the x-axis. What are you talking about? That doesn't make sense at all. Who is this Carl Friedrich Gauss person? Well, remember what he said. Has at least 1 0 in the complex number system. So let's put in a 0 for y. Negative 4 equals x squared. Take the square root of both sides, and we get x equals plus and minus 2i. Complex numbers. Lo and behold, every polynomial has at least 1, this one has 2, x-intercept in the complex number system. I mean, wow. Now you're probably saying, Kukla, what the big deal about this? Because, well, yeah, they have an x-intercept. So what? Well, if you weren't impressed by the fundamental theorem of algebra, perhaps Gauss's follow-up, the linear factorization theorem. Maybe this one will do it for you. It says a polynomial of degree n has precisely n linear factors in the complex number system. For this, they built him a small castle with servants. Yeah, I don't know if there was really a parade. I certainly like to think there was one. Tell me about this linear factorization theorem. So here's x squared minus 5x plus 6. Degree is 2. The degree n, has precisely n linear factors. And so this factors as x minus 3 and x minus 2. Look, second degree, 2 linear factors. Fabulous. But if we have something like y equals x squared plus 1, and we say, well, that doesn't have any x-intercepts. Yes, it does. X equals negative 1. X equals plus and minus I. Those are imaginary, Kukla. Yeah, but guess what? X minus I, x plus I. 2 linear, because these are first degree, factors when n equals 2. That's his linearization linear factorization theorem. Now, both of these are kind of incredibly obvious to us now. But in the early 1800s, ooh-wee, yeah, that was groundbreaking stuff. And so we know already the joy of, well, I really want to have this polynomial factored because once I have it factored, I can graph that polynomial pretty fast. Now, that being said, if my polynomial is something that has plus and minus 2i and x equals, but also 4 and negative 3. You know, I'm not expecting you to try and graph these imaginary roots. I will say, though, that if you are interested in learning how to graph with these, come into an office hour session sometime and say, Kukla, what is this thing you know about graphing on a real number graph these imaginary numbers? It's very old school. It's very cool. But really, you know, if this class were honors pre-cal, we might take a look at that one day in our class and have you do it. But for us, I'm going to be fine with just graphing the real ones. Yeah, so let's not worry about graphing those imaginaries at this time. Okay, so will you find the factored form for x to the fourth minus 10x squared plus 9? Welcome back. Did you factor this the way you would factor this quadratic trinomial with x minus 9 and x minus 1, except with this one, instead of x's going here and here, we need x squareds. X squared minus 9, x squared minus 1. By the way, this is not linear factors. We are not done factoring this. You would get this mark wrong on your test if you stopped here. Because look, we were told linear factors, and I see the difference of squares. And if you don't see the difference of squares, please go back to that video in Algebra Basics. Oh, look, another difference of squares. X plus 1, x minus 1. Okay, so there's our completely factored form. All right. I think you owe me one. Y equals 3x to the third plus 2x squared minus 3x minus 2. And yes, that x was a 3. Pause the video, write me the linear factorization of this. Okay, so good, grouping, definitely. Pull out an x squared, and then I get 3x plus 2. And here, I'm going to pull out a negative 1, because remember, I want this to be the same as that. And right now, I see these signs are opposite of these signs. So if I pull out a negative 1 from each of these, if I divide each of these by negative 1, I'll get that. These are the same. So now I have x squared minus 1 times that common factor 3x plus 2. Not done yet. Look at that. Difference of squares. 3x plus 2, x minus 1, x plus 1. And from here, no problem to graph. At least I hope that's the case. And if it is a problem to graph, you should probably ask some questions about that. Okay. All right. So now that was if we were able to factor it. So 1, try factoring. 2, we can't factor, sad face, but we are given a root or x-intercept. Well, in this situation, we're talking about this kind of thing. Y equals x to the third minus 6x squared plus 11x minus 6. And the angel of mercy comes to us and says, by the way, x equals 3 is an x-intercept. Okay, so what do I know then? Well, I know that if I do synthetic division with 3, I should end up with a 0 over here. 3, 9, 2, 6, 0. Fabulous. So given that seed, that start, even though I wasn't able to factor this by grouping, I could do some synthetic division, go from a third degree polynomial here to a second degree polynomial here, and then I could factor that x minus 2, x minus 1, and don't forget the original x minus 3. Many students leave this as their answer, but we started with a third degree polynomial, so this needs to be a third degree polynomial that we write in factor form. That's only a quadratic. We need that original seed turned into a factor so that we get the completely factored form. Okay, so that's kind of convenient when I'm given one of the roots to start with some synthetic division. I can finish it up and it'll work just fine. Okay, so what about y equals x to the third plus, I don't like that. Yeah, all right, I'll do that one while I think of this other thing. Minus 2x minus 6. And what I was thinking was, but we could just do this by grouping, so why bother to show it when I'm given a root? Well, because I'm going to be given this root, and I just wanted to see what would happen then when I did synthetic division. -2, -6. So we've got that 1, and then we multiply, and we get a 0, we get 0, and -2, and a positive 6, and a 0. Remember, this was x to the third. We divided by x plus 3, and now we're now at x squared. And so we're looking at this polynomial. And can we take that down further? Well, if I set this equal to 0, I get x squared equals 2. If I take the square root of both sides, I get plus and minus root 2. Okay? So my factored form then would be x plus 3, x minus root 2, x plus root 2. Now, what if instead of being given that 3, we had been given root 2? Okay, we need to be able to deal with that. 1, and I just multiply. Look, I know you're not comfortable with this radical here, but stop fretting about it. The fretting is just making it harder. You really do know how to do this. 1 times root 2 is root 2. And you can't add these because that doesn't have a radical, but that does. Your middle school teacher taught you that. So I have to write 3 plus root 2. What's the big deal? It's not root 5. That doesn't have a radical. Okay? Now I need to multiply this times this. Root 2 times 3 plus root 2. Well, we all know distributing. So that's 3 root 2, 3 times root 2, plus root 2 times root 2. What's that going to be? Well, I got a pair of 2's, and guess what? One of them can make it out. So that goes here. 3 root 2 plus 2. And then remember we add here. So I add minus 2 and plus 2 and they cancel, and I'm left with 3 root 2. Finally, I'm going to multiply root 2 times 3 root 2. Root 2 times root 2 is 2, times that 3, I get 6. And so that, and now that. Well, that's great. But look, this is x squared plus all this stuff x plus that. I don't want to try and factor that, which is why it's really important for us to remember that irrational roots always travel in conjugate pairs. So if root 2 works, then negative root 2 works. Okay, let's get that. 1, so we get negative root 2. Oh, look, I add these, and I'm left with this, and I multiply, and I add these, and I get this. And look, there it is. 1x plus 3 times x minus root 2, x plus root 2. Hold on a second. Yeah, that's correct. All right. So, yes, I know we could have done it that way, but really I wanted the excuse to take a look at something like this and still get that factored form, because you're going to see more of that today. Okay. So that's kind of fabulous when I'm given an x-intercept. So how about this one? Y equals 2x to the fourth minus x to the third plus 7x squared minus 4x minus 4. That's not going to be done with grouping. I don't know how to factor that one. So, can I give you an x-intercept? Well, I'll give you an imaginary root. So, 2 minus 1 plus 7 minus 4 minus 4. Down the 2, multiply. I get 4i. This doesn't have any i's. This does. I can't do anything but write that. Now I have to multiply this times this. So I'm looking at 2i, negative 1 plus 4i. And I distribute. I'm going to have negative 2i, and then 2 times 4 is 8. I times I is I squared. Remember, I squared in that, was it the last video? Yes, it was the last video. In the last video, we said I squared was negative 1. So I get this minus, this plus 8 times negative 1, or negative 8 minus 2i. So when I multiply this times this, I get negative 8 plus 2i. Negative 8 plus 2i. And I add these together. No, I can't add this with this because this has an I and this doesn't. But I can add these and get negative 1 plus 2i. So what is it that I need to do now? I need to take this and multiply it to this. So 2i times negative 1 plus 2i, and I distribute with negative 2i. 2 times 2 is 4. I times I is I squared. Well, we just said that I squared was negative 1. And so I end up here with minus 4 minus 2i. And then I add these. Now I'm going to have negative 8 minus 2i. I'm holding my breath, because somehow when I multiply this times this, I should get that very real number over there. I'm a little scared right now. I think I made a mistake. This looks so weird. Okay, so let's distribute. Oh, look. You know, you got this negative 16i. That's not going to work. I think I have a sign mistake right here. I think this is supposed to be plus. I think this is minus 2i plus 2i times positive 2i, and I think that's going to give me that. So let me go back, please, to this place. That is negative 1, and that is 2i. If I multiply this times this, I got 8i squared, which is negative 8, and this makes, negative 1, negative 2i. Okay, and that might explain why I had an issue over here finishing the problem. So I want 2i times negative, no, I'm still going to get I still have that 4 to do. So I distribute negative 2i minus 4i squared. We said I squared was negative 1. We've got negative 1 times negative 4 is positive 4. So negative 2i plus 4. Aha! They cancel. I have negative 2i. I multiply it by 2i. And I see I get negative 4. And then I times I is I squared, which is negative 1. And so negative times negative is positive 4. And lo and behold, we get 0. And that's great. You just have to be a little patient with us. Now we've gone from a 4th degree polynomial to a 3rd degree polynomial. Hey, can you do that by factoring by grouping? Yeah, I'm a little uncomfortable with that prospect. I certainly see I could take a minus 2i out of each of these, but no, I don't see the minus 2i there. But remember, just like rational roots always travel in conjugate pairs, imaginary roots always travel in conjugate pairs. Bring down that 2 and I'm multiplying at negative 4i. So what am I bringing down? Just like negative 1. I'm multiplying here, and I'm getting 2i. Oh, look, when I have those, they cancel. So I bring down that negative 1, and I multiply here. And, excuse me, no caller ID. And then I multiply, and I get plus 2i and 0. So whenever I get that 0 from the division, I get the situation where I know that these are roots of this. Now, how does that help me? Well, look, I want to factor this thing. Look what I've got here. This is x to the 4th, this is x to the 3rd, this is x to the 2nd. And now we factor this. We've got a 2x and our x. I have a 1 and a 1. I want a minus going to the 2x and a plus going to the 1x. This is not the complete factorization. Don't forget these. We have x minus 2i and x minus a minus 2i. And so there's our completely factored form. Okay? X times x times x times x makes x to the 4th. And yes, you do need to be able to do that on our polynomials test with irrational numbers like square root of 3, and yes, with complex numbers like 2i. And, let's take a look at this one. X to the 3rd minus 7x squared minus x plus 87. And I'm going to tell you that 5 plus 2i is 0. Okay, so, well, we can do this one of two ways. You tell me which you like better, okay? We know that these roots always travel in complex conjugate pairs. So if this is a 0, we also know that this is a 0, okay? This is one way to think about this problem. I've got two things that I can divide into this. So let's go. Come on, synthetic division. 5 plus 2i into 1 minus 7 minus 1 plus 87. Okay, so bring down the 1, multiply, 5 plus 2i. So we have minus 7 plus 5 is minus 2. Nothing happened to that plus 2i, so it better be there. And now I have to multiply this stuff times this stuff. And that sounds a lot like foiling to me. Okay, so I FOIL, I get negative 10, negative 4i, plus 10i, plus 4, I times I squared. Remember, I squared is negative 1, so this is going to be negative 1 times 4, which is negative 4, minus 10, I get negative 14, and then minus 4i plus 10i will be 6i. So over here, I'm going to write negative 14 plus 6i. I add these together. That gives me negative 15 plus 6i. And guess what I have to do now? Now I have to take this and multiply it by that. 5 plus 2i, negative 15 plus 6i. So negative 75 plus 30i minus 30i. And then here we've got 2i times 6i, which is going to be 12i squared, or negative 12. If I combine like terms, lo and behold, I get negative 87. These middle terms cancel. Ta-da! Okay, so I went from a third degree polynomial to a second degree polynomial. I don't want to try and factor this, but I do know that these travel in conjugate pairs. So let's go now with 5 minus 2i. Bring down the 1, multiply, I add. Negative 2 plus 5 is 3. 2i minus 2i is 0. So no i's here, just 3. Now I'm going to have to take this stuff and multiply it here. And 3, 5 minus 2i. I'm going to get positive 15 minus 6i. And look, 0. So that becomes x plus 3, x minus this 5 minus 2i, x minus this 5 plus 2i. I'm okay with you leaving it in this form, though some people like to distribute. I don't need you to distribute them. Wow, look, even with complex numbers, I can do this same synthetic division and end up with factored form. But you may remember I said I can show you 2 different ways to do this problem. And really, I just need you to know one of these 2 ways. So pick the one you like best. Okay, so what's this other magical way? Well, it works like this. We know we were given this root, so we also know that its conjugate exists. So what I want you to do is to take these roots and turn them into factors. 5 plus 2i times x minus 5 minus 2i. When we write the factors, we always start off with x minus. Like if I knew my x-intercept was at negative 1, I would write x minus a minus 1. Of course, I would change that to x plus 1, but to start with, my factors are always x minus that x-intercept. Okay? Distribute. X minus 5 minus 2i, x minus 5 minus a minus plus 2i. Hey, look, we did this in the Algebra Basics unit, except not with complex numbers. So we need to start FOIL. This times this times that, and this times that. 2x. Okay, what else? Well, now we're going to do this times this times this, and this times that. So we're going to have negative 5x plus 25 minus 10i. And then finally, I have to do this times this times this, and this times this. So what's that going to give me? Well, negative 2xi, and then this times this is going to be plus 10i, because negative times negative is positive. And then this times that. Negative 2 times positive 2 is negative 4. I times I is I squared. I squared is negative 1 times that negative 4, and I get plus 4. Okay? So let's combine some like terms now. We can cancel these. We can cancel these. And so it looks like I get x squared minus 10x plus 29. Okay. So I was able to take these 2 and turn them into this. Now, why would I want to do that? Well, we didn't just learn synthetic division 2 lessons ago. We learned long division too, and we know that we can divide this quadratic into this cubic. So I've got x squared minus 10x plus 29 goes into x to the 3 minus 7x squared minus x plus 87. What do I multiply this by to turn it to this? X. So I get x to the third minus 10x squared plus 29x. And then I subtract. Remember, long division, it's always subtract. Minus a minus is plus. Minus 7 plus 10 is 3x squared. And then minus x minus 29x is going to be minus 30x. And don't forget to bring down that 87. Now, I'm thinking that it's pretty bleak over here right now. Am I somehow going to be able to get that? Sure, look, what do I multiply this by to turn it into this? Positive 3. So when I distribute that 3 to each of these, I get 3x squared minus 30x. And you know what 3 times 29 is? And so now when I subtract, I get a big old 0. Look, there it is. So we know then that the factored form, I was given this, I knew they traveled in conjugate pairs, x minus 5 plus 2i, x minus 5 minus 2i, and then times x plus 3. So, note, this is conjugate, not this. Good. There's our factored form. So how did we do it this way? We took these complex roots, we turned them into factors. We FOILed those factors to get this second degree polynomial. We did long division with the second degree polynomial into this third degree to get our quotient, this first degree. And so then we were able to write the factored form. I honestly don't know which one I think is better. Sometimes I feel like one is better than the other, but I haven't, even after all this time, I still don't have sort of a guideline. And so what I'm going to say is, there's some work with both of them. You definitely have to be wicked careful about sign mistakes and multiplying stuff with both of them. But I do know that both of them always work. So either you're going to take these imaginary roots, 5 plus 2i, and say, oh, look, they travel in conjugate pairs. You're going to turn these into factors, x minus 5 plus 2i, x minus 5 minus 2i. You're going to FOIL this out. When we did, I believe we got x squared. I don't remember if that was minus. I think it was minus. I think it was minus. I know this was 29. Is this 3? Oh, I've lost it. And I'm certainly not going to take the time to do that again. We would FOIL this out. We'd get the second degree polynomial. We'd get this x squared. Oh, just so close. And there's that magic 29 that came to rescue us. And I would divide this with long division into my original polynomial to find my last factor. So that was the second way. The first way, 5 plus 2i, and then 5 minus 2i into our original function, put this one, and then we'll get this quotient, and into the quotient I do the conjugate one. Okay? So, okay, so we can factor stuff. I mean, we can break down some scary polynomials. Not a problem. So what that method, though, depended on was me being given a root. Me being given a root. In all of these situations that we were just talking about, I had to be given a root. Once I was given a root, I could do synthetic division with the conjugate pairs, or, for example, here, x minus root 2, x plus root 2, because they always travel in conjugate pairs. And then I could FOIL this out and divide that x squared minus 2 into my function to get something that maybe I could factor. Okay? So that's definitely something that we can do. We can turn those irrational and imaginary roots into factors. We could then take those factors and FOIL them together and then do some long division. Or we could actually take 2i and divide in synthetically, and then negative 2i, and to divide into the quotient synthetically to get something down here that will be factorable. But all of this depends on someone giving me a root. Well, the world is sometimes a kind of mean place. So it may well be that I'm given a problem like this, x to the third minus 7x squared minus x plus 87, and I'm not given any roots. And that's pretty much as far as we're going to take this. What happens if someone says, hey, I need you to graph this, and doesn't give me one of the roots, whether real, whether imaginary? I'm just not given any of the roots. Now, I will say that there was this really nifty old school method where we would take this number times this number, and we would say we would say the factors of this number over the factors of this number are going to produce, if there are any rational roots, real rational roots, then I know the factors of 87 over the factors of 1, which is 87, which is 29, which is 3, 1 over plus and minus 1. And so then I've narrowed it down from this thing could have, I don't know what x-intercepts this has. I do know that every third degree polynomial could have one x-intercept, or we could have two x-intercepts, bounce, doink, or we could have three x-intercepts, 1, 2, 3. So if there are any real ones, and I have to have at least one real one, I could have one real and two imaginary, then it's in this list. I mean, you know, this was terrible stuff to do because we don't know which. We've narrowed it down from an infinity of numbers to choose from to simply 8 numbers to choose from. If there are any real roots in this polynomial, and we know there must be at least one, thanks to our fundamental theorem of calculus, fundamental theorem of algebra, we know there's one, and so at least one of these 8 numbers will work in here with synthetic division. And what I mean work in here with synthetic division is that if I take that number, like negative 1, 1, negative 7, negative 1, 87, and I do my synthetic division, that's 8, that's 7, that's oh look, I got positive 80, that's not 0, so that's not a root. And yeah, I didn't find one, which means I need to keep trying the other ones in the list. So this was really time consuming, but it was very dependable. And about 2 years ago, I stopped teaching kids about the factors of P over the factors of Q. I believe it's in our textbook, but look, you're not going to be asked this on the event math placement test. You're not going to see this on the ACT. And so really what I want to say to you is, in a situation like this, where someone does not give you one of the x-intercepts to start doing your synthetic division with, or you can't factor that, say, by grouping, in that case, our new strategy, instead of that old school P and Q thing, is graph on the graphing calculator to read a real x-intercept off the calculator graph. Okay, so that's what I want to be doing. Now, we know with this problem that negative 3 is one of our roots. And I forgot to bring a calculator in with me today, so I think I'm going to quickly try and do this with Desmos. Yes, I do know what Desmos is, even though I seem to be a TI stooge. But there are some things that the TI can do that I've never figured out how to do on Desmos. But if we graph x to the third, so I want x to the third, and then I want minus 7x squared, minus 7x squared, good, minus x, and then plus 87. Okay. Now when we look at this, see that shape? That's the thing I told you if you want to come into office hours. This is definitely the effect of those two complex roots in here. But I do see only one x-intercept, -1, -2, -2. And so I read that x-intercept off the graph, and then I go about my synthetic division business. 1, -3, -10, +30, +29, -87, and 0. So now I've got this, 1 minus 10 plus 29. Remember, this is now a second degree polynomial. I divided my x to the third by x plus 3, and I ended up with an x squared here. So, now that I have that x squared minus 10x plus 29, can I factor that? Yeah, I can't factor that. So what am I supposed to do then? Well, I want to find the factored form. If only I could find the zeros, the x-intercepts. Well, wait. I've got a quadratic. X equals -b plus and minus square root. X equals -b plus and minus square root of b squared minus 4ac all over 2a. All right. Where does that take me? 10 plus and minus square root 100 minus, this is 80, and 36. Isn't that 116? Did I miss it though? Ooh, scared puppy. 4 times 25 is 100, and that's going to be a negative under the rank. I feel so scared. Don't worry. We already know that we're supposed to get imaginary root here. No, really, we do. Because look, square root of -16 is the square root of -1 times the square root of 16. And that's I, and that's 4. So I'm going to have 10 plus or minus 4i over 2, which I could write as 10 over 2 plus and minus 4i over 2, which is 5 plus and minus 2i. Look, there it is. Those were the complex factors, complex roots that we talked about when we did this problem the first way. So, let's see if we can sum this up. 1, factor with your factoring skills. 2, someone gives me a root and I do synthetic, though sometimes you might want to do long division with it. And then what did we just talk about? The 21st century approach, graph on calculator. Oh, let's be explicit here. Not given a root. And when we're not given a root and we can't factor it, then I do want you to graph on the calculator and read and x-intercept off the graph so that then you can do that long or synthetic division. Okay? All right. I think it's time for us to do some practicing. Ready? Okay, here we go. So, will you please, y equals x to the third minus 11x squared plus 6x minus 1. Will you write the factored form of that? And of course, a graph would be nice as well. Look, it was just on the last whiteboard. Think about those 3 strategies I listed. The first one, can you factor this with factor by grouping? No. Move on. Second strategy, take a root that was given to you and divide it in with synthetic or long division. Were you given any roots? No, you weren't. Number 3, I can't factor it. No one gave me a root. What am I supposed to do? Aha! You are supposed to pull out your graphing calculator and you are supposed to take a look at the graph. And what I see is I've got 1/3, I've got 1/2, and I've got 1. So I'd like you to read one of those x-intercepts off the graph. I want you to take this and do some synthetic division to break that down from a 3rd-degree polynomial to a 2nd-degree polynomial. Notice in that one I went for the whole number and not for the fractions because you're just going to be looking at decimals and then you're going to round those decimals. You're not going to turn them into fractions. Because of that, it won't work if you use those others. So instead, I saw that 1 was a root. 1, -11, 6, -1. 1, -10, -10, positive, whoops, -4, negative, whoop, no, that's not right. I think I have a typo somewhere. Plus 6x minus 1. Okay, so what am I supposed to have? Oh, I'm supposed to have a 6 here. Oh yeah, I'm going to hold that thought a moment. Minus x plus 1 times x minus 1 minus 6x squared. No, x squared plus 2/3 5x squared plus 6. Minus 6x squared plus x and minus 1. That's going to give me 6x to the 3rd minus 11x squared plus 6x minus 1. Yes, I did leave out that 6. Very good. X is pressed on 6. Okay, so this is actually a 6. This is actually a 6. This is a 6. So this must be a -5. Put that -5 here. -1. This then becomes 1, and I do get 0. So where do we go next? Well, this is 6x squared minus 5x plus 1, because this has to be 1 degree less than what I started with. And here, can I factor it? Well, yeah, I like to think you can. 2x, 3x, 1, 1, minus, minus. This is not the complete factorization. Don't forget the original divisor. Okay? It's a really common mistake on the next test. We need to be able to FOIL to get a 3rd-degree polynomial. If you only have this, you only have the 2nd-degree polynomial. So remember, that strategy was, if you can't factor it and no one gives you something to start your division with, the expectation is that you're pulling out your graphing calculator and you're reading one of the x-intercepts off the graph. All right? I really wish you were here with me right now, because I'd like to get a sense as to whether you want another one of those or something a little harder. So I'm going to go with something a little harder. I'm going to say, I'm going to say this one. Y equals 3x to the 3rd plus 15x squared minus 21x minus 35. Is that factorable? Oh, maybe this isn't so bad after all. Let's see what happens when we do grouping. We take out a 3x squared. We're left with x plus 5. We take out a -7. And we have 3x plus 5. Did I do something wrong? No, I took a 3 out of both of those. Yeah, I think I have a mistake here. I'm going to bail on this one. Okay, let's go to something more humane. Or is it? So here we've got y equals 3x to the 3rd plus 14x squared plus 20x plus 8. Okay, this won't factor by grouping. You're welcome to try it. But what I see is I'm going to take out an x squared and have 3x plus 14. And I look over here and say, I can't get that to be 3x plus 14. So no one gave me an x-intercept. I can't factor it, so I need to take out my graphing calculator and graph this. And when I do, I see there's an x-intercept at -2. So 3, 14, 28, 3, -6, 8, -16, 4, -8, 0. And now I know that this is 1 degree less than the one I started with. And now I've got this quadratic, and I like to think I can factor that. 3x, x, 2, 2, plus, plus. 2x and 6x makes 8x. 3x times x is 3x squared. 2 times 2 is 4. Well, so that's all good. But look at that. Do we have the complete factorization? No, we need third degree. So we want x minus a minus 2, which is x plus 2. I've got another x plus 2 over here, and then my 3x plus 2. And what can we do with that? Multiplicity of 2. Did we see the bounce on this graph at x equals -2? Right. I shouldn't be surprised. If I see that bounce, then I know that this is going to work again. And so I get -6, +2, -4. Ta-da! There's that third factor. And I'd use this one twice. So x plus 2 twice, and a 3x plus 2. Ta-da! All right, so what about this one? Say we'll do 2 more. Let's try 2 more. All right, how about this? I've got y equals, kind of want to do that. All right, easy one first. 3x squared plus x minus 3. So I want this in linear factors. How do you do that? Well, yeah, I'm going to factor, because look, I got these 4 terms. I take out an x squared. It leaves me x minus 3. Here's an x minus 3. Oh, great. You have to factor something out, even if it's just a positive 1. So now I have these 2 terms, and they both have this common factor. Take out that common factor, x minus 3. Now what am I left with? Well, I'm left with this x squared and this plus 1. So here I have x squared plus 1. Even though I've started factoring this, this is not linear factors. This is quadratic. So x squared plus 1 equals 0. X squared equals -1. Take the square root of both sides. Remember, you take the square root of both sides. You need to remember that plus and minus. Oh, why is it I? Square root of -1 is I. So my factors then, x minus 3, x minus I, x minus a minus, or x plus I. There's our factored form. I want linear factors. Please know x squared sitting there, that's just saying, hey, you're going to get this wrong because you didn't take it far enough. Okay, and our last one. Let's take a look at our last one. How about this? Y equals x to the third plus x plus 10. Yeah, you know, if this were x squared, I might think I had a fighting chance of factoring it, but no. And I got no x squareds here. So, what do I have to do? I can't factor it. No one gave me an x-intercept. I'm supposed to pull out a magic box, graph it on the magic box, and see, look with my eyes and see that there's an x-intercept at -2. And once I know there's an x-intercept at -2, I can do some synthetic division. Now, before I write the rest of this down, can anyone tell me what it is that a lot of people are going to forget for this synthetic division? Oh, 0 placeholders. Very good. We have x to the third, we have x to the first. Where's our x to the second? Okay, so you have to have that 0 placeholder there, 1 and 10. Or guess what? It doesn't work. Great. So now we've got x squared minus 2x plus 5. Can you factor that? Yeah, me neither. But what I can do is use the quadratic formula on this, find the x-intercepts, and then turn those x-intercepts into factors. So let's see what that looks like. Okay, we're now going to work with x squared minus 2x plus 5. Okay. We know that x equals negative 2 is one of our roots, and we're now looking at this saying, okay, x equals negative b plus and minus square root of b squared minus 4ac all over 2a. So that's 2 plus and minus square root of, this is 20, 4 minus 20 is negative 16 over 2. Square root of negative 16, we are not scared about the square root of negative 16. We are thinking about square root of negative 1 times the square root of 16. This is 4, this is I, and so I get 2 plus and minus 4i over 2. Please, by all the gods that have ever existed, do not do that. I will come to your home. I will chase you around the living room with a pool noodle. I know Mike Davis wants to try it just to see if I'll come. I promise, Mike, I'll show up with a pool noodle. Okay, but what I can do is this. I can factor a 2 out of the top. And I can cancel with the 2 on the bottom. You have to be able to take it out of all 3 in order to cancel it. You can't just cancel these, right? It has to be, I can take a 2 out of each of these. What will I be left with? 2 divided by 2 is 1. 4i divided by 2 is 2i. 2 divided by 2 is 1. Okay? I can cancel, but not just some of this stuff. It has to be all of this stuff. So we've got 1 plus and minus 2i. Remember what we were trying to do? We were trying to write the linear factorization of this third-degree polynomial. We looked in our calculator and saw an x-intercept at negative 2. Now I've got these two complex numbers, x minus 1 plus 2i, x minus 1 minus 2i. So x plus 2, x minus 1 plus 2i, x minus 1 minus 2i. And there's my factored form. All of these are x to the first, so I have linear factors. You know, there are some teachers who will want you to distribute that. I don't need you to do that. I think this is plenty of work. All right, so you are fully armed. You are so well prepared. You've got this down. You know 3 things. 1, I can get it factored with my factoring skills. 2, some benevolent angel will give you one of the x-intercepts or one of the roots so that you can start some synthetic division or long division. And 3, last choice, is you pull out your calculator, read one of the x-intercepts on the graph. Now look, let's imagine that you had x-intercepts at 1/3, 1/2, and 1, yeah? So you graph this, because you couldn't factor it, right? So you graphed it and you said, oh, there's 1 and there's these other 2. And let's say you are able to read all the x-intercepts off the graph. And so you say, oh, there's my factored form. And you haven't shown me any work. I'm marking it wrong. Why, Mr. Kukla? Well, look, see, what I'm really doing here is allowing you to use the magic box to get a start on the problem, because I don't want you to have to suffer through P's over Q's. We are in a different century now. But the compromise is this. I'll let you use your graphing calculator to find a real root, but then you have to show me some longer synthetic division using that root to find the other 2. I do need to see some work. It can't just be I see this on the graphing calculator screen and I turn that into 3x minus 1, 2x minus 1, and x minus 1. Because really, that's great. But I'm actually asking you to go a little beyond that, since I'm letting you pick up the calculator, use it to find a root. You know, if it's 4th degree, find 2. But I do need to see some work on those problems. All right? So that's about as tough as that gets. Word problems come